Hello and welcome to another lecture of Learning with Funke. Today we're going to be going over enzyme kinetics. First of all, let's talk a little bit about the Michaelis Menten equation. And so we must have seen this equation on the left a couple of times. I'm just going to go over, first of all, as a quick introduction, what these terms represent. So when we see the Vmax typically represents the max reaction rate, which corresponds to the velocity at which, the maximum velocity at which enzyme converts, substrates to products. And Vmax prime is the apparent Vmax, right? So usually would use Vmax prime under experimental conditions where there is an added inhibitor. So sometimes Vmax prime equals Vmax, and sometimes Vmax prime may not equal Vmax, right? Based on the mode of inhibition going on. So same thing, let's go to Km. Km is typically used to represent an inverse measure of affinity. So what that means is if you have high affinity, you would expect low Km values. And if you have low affinity, subsequently you would expect high Km values. So it's kind of like that inverse proportionality going on. And so Km is used to represent like the strength of binding between the enzyme and the substrate. So like I said before, the lower the Km, the greater the affinity, and so the lower the concentration of substrate that is needed to achieve that given rate. And similar to the Vmax prime, Km prime is the apparent Km. So literally the same thing. Km can be equal to Km prime, or it may not be equal to Km prime, depending on what the mode of inhibition is. And similarly, Km prime is used to represent the Km when we have added inhibition going on. So yes, so that's kind of like what we show on the screen here with respect to the graphs. And so if you look at this, when you take the limit as substrate goes, increases and goes to infinity, you can approach this Vmax value. And similarly, when substrate is at 0, you have a 0 rate. And so let's go into some background also on what we mean by, so what is competitive inhibition, what is non-competitive inhibition, and what is uncompetitive inhibition. So for the first one, competitive inhibition, so think of it, so when you have an enzyme and the active side of the enzyme binds to the substrate, right, that gives you the product. However, in the flip case where you have an enzyme that binds to a competitive inhibitor, that kind of blocks the active site from interacting with the substrate. And so, in other words, competitive inhibition refers to the type of inhibition where the active site of the enzyme is occupied by a substance aside from the substrate of that enzyme. And so this is usually the competitive the inhibitor, and this inhibitor is usually structurally analogous, so it's structurally similar to the substrate, such that it can bind in the place of the substrate. And so in such inhibition scenarios, what you would find is that you would have both the enzyme substrate and the enzyme inhibitor complexes being formed. And in other words, you would also see that the Km increases, but the Vmax will stay the same. So what I mean by that is it would still approach the same Vmax, but it would take longer to approach that same Vmax, right? And so in other words, you have a shift to the right where that Km value is increasing because you need more higher concentration of the substrate to achieve that same Vmax value. And when I say Km increases, it increases by a factor alpha. We'll get to see this alpha factor a couple more times during this lecture. But alpha is typically this equation in brackets, so it's just 1 plus I over Ki. And so it's usually Km prime equals Km times alpha, where alpha is just this value here, 1 plus I over Ki. And so in other situations where, if Km is decreasing, it would also decrease by alpha, right? But in those situations, instead of Km times this alpha, it will be Km divided by alpha. That's something that we'll be going over later on, but it's good to, point that out now. So we have that at the back of our minds, how, Km prime changes when we have inhibition. In this case, it's competitive. So since Km prime is increasing with added inhibition, we have that Km times alpha, right? Because it has to increase. One other thing to pay attention to is that when we have competitive inhibition, you would have to increase the amount of substrate, right, to force any think of it as majority wins, right? So you'd have to increase the amount of substrate to pretty much force inhibitors out of that active site of the enzyme. And so kind of like how it all ties together, you have to increase that substrate concentration to reverse the effect of any inhibition going on. Yep. So yeah, like I said here, the extra substrate makes the substrate molecules abundant, like a majority winning scenario, such that it's enough to consistently beat the inhibitor molecules to the enzyme. So when you see inhibition modes where by increasing the concentration of the substrate, you're able to reverse the inhibition going on, then you can think, oh, that has to be competitive inhibition, right? Okay. And so for non-competitive inhibition, the substrate is still binding to the active site. However, your non-competitive inhibitor binds to a separate allosteric site. So it doesn't bind at that active site. And so in this scenario, right, if you have this inhibition going on, even if you increase the concentration of the substrate, it doesn't necessarily affect it doesn't reverse the inhibition, right? Because the sites where they are binding are different. And so in this case, what is changing here now is not the Km. So Km here is equal to Km prime, right? Because changing the substrate concentration doesn't affect that inhibition. But what we see here is that the Vmax, right? The highest or maximum rate that you can achieve reduces, but your Km prime is still the same as Km. And so the inhibitor binds reversibly with the enzyme site other than the active site. Inhibitor may combine with both free enzyme and the ES complex, but overall Vmax prime decreases once again by this factor alpha, and that's why Vmax prime equals Vmax divided by alpha. However, your Km value is not changed, right? So your and then to the next point, strong affinity for inhibitors prevent catalysis, possibly due to distortion in enzyme conformation. And to finalize for this, with a non-competitive inhibitor, the reaction can never reach its normal Vmax value. So Vmax is not equal to Vmax prime. Vmax prime is equal to Vmax divided by alpha. Okay, and that pretty much wraps it up for non-competitive inhibition. Okay, and now for the last mode of inhibition, uncompetitive inhibition. This is another different mode of inhibition in the sense that the inhibitor binds to the ES complex. So the substrate has to first bind to the enzyme, and then the uncompetitive inhibitor binds to the ES complex, right? It doesn't bind to the free enzyme. And so the formation of this EIS complex, so like the enzyme inhibitor substrate complex, will prevent further catalysis from going on. And so we can convert that enzyme substrate complex to product, right? And in this case, we have Vmax decreasing, right? We also have Kmax decreasing, and they both decrease by this same constant alpha. And so in this case, remember how I said if it's decreasing, you're dividing by alpha. If it's increasing, you're multiplying by alpha. In this case, both constants are decreasing by alpha, so it's Vmax prime equals Vmax divided by alpha, and Km prime equals Km divided by alpha. It's important to note that in this case of inhibition, we have both Km and Vmax decreasing. However, they both decrease by the same factor. That is very important. So when you see Km divided by Vmax, or Vmax divided by Km, in these scenarios, the ratios are always constant. So Vmax over Km will be equal to Vmax prime over Km prime in the presence of inhibition, right? Because even though Vmax prime and Km prime are both decreasing, they are both decreasing at the same ratio, this 1 plus I over Ki. So the ratios end up being the same. And that's something that I've seen that, some of my students get confused a couple of times. It's important to understand that Kmax decreases, Vmax decreases, but they both decrease at the same ratio. So ratios of Vmax to Vmax prime to Km prime, or Km prime to Vmax prime, would always be the same as Vmax over Km. Okay. And so pretty much looking into, competitive versus non-competitive versus uncompetitive. This is a quick summary slide. So for the direct Michaelis Menten plot, so for competitive, we see that the Km shifts to the right, right? We achieve the same Vmax, but we achieve it at a higher substrate concentration. So our Km prime is equal to Km times alpha, right? Because we have that Km increasing to the right. Now for non-competitive, we have less Vmax, right? Because we are not achieving that same Vmax that we achieved before. Now, this is the scenario where we talked about where the inhibitor is not binding to the active site, right? It's binding to the allosteric site. So we are reducing Vmax, but by increasing substrate concentration, you're not really changing the inhibition, right? Since the sites are different, right? So in this case, the Km is still Km prime, but your Vmax prime reduces. So your Vmax prime becomes Vmax divided by alpha. And then in uncompetitive, we have both cases, right? So Km prime is reducing. We also have Vmax prime reducing, still by that same factor alpha, such that if we have to take their ratios, those ratios are constant, right? Compared to Vmax and Km. All right. And then we're going to go into like the different types of linearization plots later. But this is just something to give you like a early insight on like how this will change. So for competitive, we know that Km prime increases, right? So here we see that 1 over Km is the x-intercept. And so because 1 over Km is the x-intercept, in the case where we have inhibition, right? 1 divided by a bigger number, since Km prime is increasing, 1 divided by a bigger number is a smaller number. That's why you see that the x-intercept kind of shifts to the right. However, the since Vmax is the same, and this y-intercept is 1 over Vmax, for both of them, they would have the same y-intercept. And that's why you see that change, right? Same thing for non-competitive, we say that Km is equal to Km prime. So that x-intercept, which is 1 over Km, since Km is Km prime, they will both have the same x-intercept. But then because Vmax is changing, right, they will have a different y-intercept. And how would the y-intercept change? We said Vmax prime reduces, right? So Vmax prime is smaller than Vmax. And so in that case, since the y-intercept is 1 over Vmax, we're having 1 over a smaller number, right? Which is a bigger number. That's why the y-intercept in the inhibitor scenario is actually higher, right, than the uninhibited scenario. And then finally for uncompetitive, since in this case the x-intercept is 1 over Km, right? So in the inhibitor scenario, if Km prime is reducing, like we talked about before, so 1 over Km prime would increase, right? And so we kind of have that shift to the left where it becomes more negative. And then similarly, I think there should be a negative here, but similarly, when you have 1 over Vmax also reducing, Vmax also reduces, so 1 over Vmax would increase, and that's why you have the intercept increasing here. So overall, what we see is, I'm going to wrap it up with this table on the right. For competitive inhibitor, we have effect on Km, we have an increase in Km, no effect on Vmax. For uncompetitive inhibitor, we have both Km and Vmax reduced. And then for non-competitive inhibitor, we have no change in Km, right? But then we have a decrease in Vmax, okay? And then here the inhibitor is binding to, in non-competitive, the inhibitor can bind to both the enzyme and the enzyme substrate. But in uncompetitive, the inhibitor is binding to the ES, so like the enzyme substrate complex already formed, okay? Okay. And now let's go into linearization methods. We have multiple types of linearization methods, but for the concept of this class, since this was requested by bioengineering students at UMD, just to fit it into the scope of what you're learning in class, we're going to cover these 3 linearization types. Lineweaver-Burk, which is also known as a double reciprocal plot. I'll go into that why that is called that later. And then the second one is Hofstee, and then the third linearization type is Woolf. And these linearization types are pretty much just linearizing the Michaelis Menten equation, so it's easier to get those constants and fit them or get them from fitted data. Okay, so now let's look at the first one, Lineweaver-Burk. I'm going to start here on the left. So this is literally me showing how we arrive at the linearization, where you recognize this, right? This V equals V max times S divided by Km plus S. That is just the Michaelis Menten equation. When you take the inverse of both sides, you arrive at this second line here. And then that becomes Km plus S divided by V max times S. And by separating out your variables, you get 1 over V equals Km over V max times 1 over S plus 1 over V max. So using the format of Y equals mx plus b, you can see that your Y here is what? 1 over V. And your X is what? 1 over S, right? And then your Y-intercept is 1 over V max, while your slope is Km over V max. You can also solve for your x-intercept by setting your y term to be 0. So if you set 1 over V to be 0 and you solve for 1 over S, which is your x, you will find that your x-intercept is equal to negative 1 over Km, which is literally what we show here on the right. So your x-intercept is negative 1 over Km, your y-intercept is 1 over V max, your slope is Km over V max, right? And you're plotting 1 over V versus 1 over S. Okay. And so by looking at the three linearization plots, the three Lineweaver-Burk plots for competitive, uncompetitive, and non-competitive, we kind of went over this before, but you see here that because for competitive, your Vmax is the same, right? So you would expect that your y-intercept, right, 1 over Vmax would be the same. However, your x-intercept will change because for competitive, since your Km is increasing, right, your negative 1 over Km will what? So 1 over Km would reduce, right? So you would have a smaller negative value, and that's why with inhibition, you see a smaller negative value to the right, right? But keeping the same y-intercept. And then going into uncompetitive inhibition, you see here we said Km, both Km prime and Vmax prime are decreasing, right? However, you see that Km prime over Vmax prime would have, in the case of inhibition, would have the same, because they're both decreasing by the same ratio, right? We talked about how this ratio will be constant, right? So what that means is these two lines, Km over Vmax with no inhibition, and Km prime over Vmax prime with inhibition, those slopes will be the same because Km prime over Vmax prime would decrease by the same ratio. So that alpha constant will cancel out. That's why you see similar slopes, and that is indicative by the two parallel lines. You see how the inhibition slope versus the no inhibition slope, they are kind of parallel to each other. So those slopes will be the same. However, like I said, so 1 over Vmax, so Vmax in this case is decreasing, so 1 over Vmax will be higher. That's why you have the here higher, right? And here negative 1 over Km, since Km is decreasing, so 1 over Km would increase. So you would have negative 1 over Km will be a larger negative value, right? So that's why you have that increased negative value to the left here. And that's how you can pretty much sketch what you would expect these plots to look like. And same thing for non-competitive. We said for non-competitive, Km is the same. So Km equals Km prime, right? And so since Km is equal to Km prime, what will be the same? You know your x-intercept will be the same, right? Because your negative 1 over Km will be the same as negative 1 over Km prime since Km is equal to Km prime. And that's why you have the same x-intercept. However, for your y-intercept, right? Since your y-intercept here, you would have that, Vmax is actually what? Decreasing. And that's why you have, since Vmax is decreasing, 1 over Vmax will be higher. And so with inhibition, you have 1 over Vmax higher for non-competitive, right? And so that's pretty much how you would use these to, explain. And once again, your Km over Vmax is your slope. your Km is the same, right, for inhibited versus non-inhibited, but your Vmax is reducing for non-competitive inhibition. So that means your slope, since you have a smaller number in the bottom, your slope would increase for the case of non-competitive inhibition. And that's why you see a greater rise in the case of inhibition for non-competitive inhibition. So this is pretty much how you would, analyze what you would expect your graphs to look like, so that, like, even without giving data, you can kind of have an expectation of what how your inhibited versus non-inhibited plots should look like. Okay, so that's for Lineweaver-Burk. I'm going to go on to the next one, Hofstee. And in this case, I've shown also how the linearization works. Once again, we start by the inversing of both sides. However, in this case, pay attention to the y and x axis. In Lineweaver-Burk, we had the inverse reciprocal plot, right? We had 1 over v versus 1 over s. And in the Hofstee, we have v versus v over s, right? Where the y-intercept is Vmax, and your x-intercept is Vmax over Km, and your slope is negative Km. And so pretty much you can make similar analysis for, like we just made for competitive, uncompetitive, non-competitive. So if your slope is negative Km, in a scenario where you have Km is equal to Km prime, which is in the non-competitive scenario, right? You would expect that the slope for this type of linearization in non-competitive will be the same. The x and the y-intercept might change, right? Because your y-intercept is definitely gonna, for non-competitive, since Vmax is reducing, that means your y-intercept will reduce, right? So you'd have something for non-competitive where your Vmax is reduced, right? But then your slope will be the same. So those are kind of things that you would think about in terms of like how you would expect the trends to change. All right, same thing for his Woolf. Here we're also plotting something different. So in Hofstee we had V versus V over S. Here in his Woolf we have S over V versus S. So you have to know what the y axis and the x axis are for each linearization type, because based on that your slope will change, your intercepts will change. So you have to understand how that works. So here I've also shown how I arrived at getting the math to work. So here we once again start by inversing, right? Kind of like how we did for the other two. But here we have a step where after we get to this point, we are multiplying through by s. So we end up having s over v equals 1 over v max times s plus km over v max, where km over v max is your y-intercept, and you're plotting s over v versus s, and your slope is 1 over v max. So in a scenario where, let's do another short trivia. In a scenario where 1 over your v max is the same, so what scenario is that? You have v max the same for competitive, right? So if your v max is the same as in the case of competitive, you would expect that with a competitive inhibitor versus the base no inhibitor case, your slopes will be the same now, right? Because under his Woolf linearization, 1 over V max is the same in competitive. And so that's pretty much, just giving out ideas as to how like you would internally rationalize what should change and what shouldn't change. And you can do the same thing, for, the KM and the V max for, uncompetitive versus non-competitive. Okay. All right. And so the next case now is going into inhibitor studies. So we've talked about how, Km changes in competitive. We said Km increases in the case of competitive to Km prime by the factor alpha, right? We also talked about how, but Vmax in competitive is equal to Vmax prime, so that doesn't change. We also talked about how in non-competitive, right, we have this case where Vmax prime reduces by factor alpha. We talked about that earlier, where Vmax prime equals Vmax over alpha, right? So this is the case of competitive. This is the case of non-competitive, right? Because in this case, only Km prime is changing. In case 1, only Km prime is changing. Vmax is equal to Vmax prime. In case 2, for non-competitive, Vmax prime is reducing, right? But Km is still equal to Km prime. However, there's a third case that we haven't shown here because that typically doesn't, we typically haven't looked at linearizing that. But it's important to know that there's also a third case where, like we said before, the max prime and Km prime are both decreasing, and that was the case with uncompetitive, right? And so in that case, we would have a third case where this will still be the same, right? Because the max prime is still reducing. However, because in the third case of uncompetitive, Km prime is now reducing, right? So what will happen in uncompetitive Km prime? That will just be Km divided by this factor, right? Yes. So if you understand that, you're in a good starting point. Okay, so now looking at case one and case two for here competitive and here non-competitive, let's take a look at case one. So when we have to, usually what happens is when we've gotten our first initial starting point data, we've looked at, based on the inhibitor data that we're given, usually we would first analyze that and get our Km prime values. And then from those Km prime values, there's something else, that is actually very important. So we've talked about the importance of Km, helps us understand the binding affinity because the lower the Km, the higher the binding affinity. There's also this factor called Ki, right? In this case, it's similar to Km, but in this case, it's pretty much looking at the effective inhibitor concentration to achieve the same, the effective inhibition concentration to achieve the maximum inhibitory effect. So what I mean by that is similar to Km, just like you would like to have a low Km value, right? Low Km value once again means high, so you just need the low substrate concentration to achieve the max rate, right? Same thing in Ki, we want a low Ki, right? Because think about it this way, if we're trying to treat cancer, right? Kind of like what we went over in class, if you're trying to treat cancer, you want a low Ki because that signifies a low inhibitor concentration to achieve the same or a high max inhibitory effect. However, in general cases, what we know is once we know what our Km prime values are with inhibition, we typically want to calculate this Ki value. And so what happens is once we've done our linearization like we did in the previous slides, right? We usually get what? So you have different scenarios with different inhibitor concentrations, and you can use that to get like your Km prime values. Once you get your Km prime values at those inhibitor concentrations, right? Say you had two inhibitor concentrations with the base no inhibitor concentration case, then you would have three data points for your Km prime, right? The one at 0 inhibitor concentration and the ones at the other two inhibitor concentrations. Then by linearizing this equation here for the competitive inhibitor case, you see that you can get Km prime is equal to Km plus Km times I over Ki. What does that tell me? That tells me that if I can take those three data points for my Km prime and I plot it against the inhibitor concentration, I would get an equation where the y-intercept, which is like my base case of no inhibitor, right, should be Km, which makes sense. And then the slope should be Km over Ki. So if I have a graph plotting Km prime values versus inhibitor concentration values, once again, these Km prime values you get from your linearized inhibitor plots, the Lineweaver-Burk, Eadie, Hofstee, and Woolf. When you plot those Km primes versus these inhibitor concentrations, that line should give you a y-intercept that is equivalent to Km at no inhibitor plus this slope Km over Ki, which is represented here. Y is equal to B, which is a y-intercept, plus M times X, right? So here your intercept B is your Km and your slope is Km over Ki. And now from this linearized equation, we can now go on further to say, okay, I know my slope M is equal to Km over Ki, but I need to find Ki, right? Like I said before, your Ki tells you, once again, the concentration of the inhibitor that you need to achieve your max or max inhibitory effect. And we need to have this Ki low because, kind of like the example given in class, having a low Ki means you can take a small pill, right, to serve as an inhibitor in like fighting a disease, so like cancer or any other disease where you're trying to have like this inhibitory effect, right? You can have a low Ki, so you're taking that low inhibitor concentration as a drug, as opposed to taking a high inhibitor concentration where you have to take like a big, for example, just to make up for the same inhibitory effect. And so once you know that, you ideally we know that we typically want a low Ki. A low Ki is always better. Same thing, a low Km is always better for the purpose of analysis and research. But when we have this, you can pretty much just solve and do a subject of formula. Ki is just equal to what? Ki from here is just equal to Km over m, right? But then we know Km is intercept, so Ki is equal to intercept over slope. Same thing for case 2. Once you take those Vmax prime data values, you can linearize it, and I've shown how I've linearized it here, where I took the inverse of both sides. And when you pretty much follow this math down all the way to the bottom, this is how you would get the linearized case in the case of what? Of non-competitive Vmax prime reducing, which is similar to the case of uncompetitive Vmax prime reducing, right? So that will be, 1 over Vmax prime equals 1 over Vmax plus 1 over Ki Vmax times I. And here we see that the slope here, the intercept here is 1 over Vmax, and the slope is 1 over Ki times Vmax. Your Y that you're plotting in this case is 1 over Vmax prime, right? So you are plotting the Vmaxes at the different inhibitor concentrations from your previous linearized plot, similar to how we did here, versus your inhibitor concentration. So the only difference here is now your Y here is your Km prime versus your X being your I. But now here, in case 2, your Y is 1 over Vmax prime versus your X still being your I, right? And so based on this, once again, your 1 over Vmax will be, that 1 over Vmax at the condition where there is no inhibition, which we typically expect, right? And then your slope here is 1 over Ki Vmax. We know that intercept is 1 over Vmax, so we can substitute intercept for 1 over Vmax here, and that just becomes slope equals what? Intercept over Ki, right? And then Ki becomes similar to this. Ki is still intercept over slope. And then if you are given like I was saying before, like the uncompetitive case, where in that case, instead of having Km prime Km prime increasing, you're having Km prime reducing. In that case, you will just have something similar to this, but then it will be Km prime equals Km over 1 plus I over Ki, right? You will pretty much follow the same linearization step, but you can do that as a self-practice. But for general cases, this will be case 1 is the competitive case, and case 2 is the non-competitive case, right? Okay. And so that brings us to the end of like the this lecture. And so overall, we've gone over Michaelis Menten. We've defined what the parameters are, Km versus Km prime. We talked about how, Km can be equal to Km prime. Km might not be equal to Km prime. It all depends on the inhibition mode. Same thing with Vmax. Vmax might not be equal to Vmax prime. Vmax might be equal to Vmax prime. It all depends on the inhibition mode. So you have to know what the inhibition modes are, and you just have to know that these are just Km just represents the substrate affinity. With Km there's no inhibition, but with Km prime now we're including inhibition. Same thing for Vmax versus Vmax prime. Vmax prime, we're just having added inhibition. Vmax is pretty much the base case where there is no inhibition. Okay. And so we've also talked about competitive versus non-competitive versus uncompetitive enzyme inhibition. We talked about competitive, where both the enzyme, the inhibitor, and the substrate are both competing for the active site. And so typically the way you would overshadow that inhibitor is by adding more and more of the substrate, right? So that it can beat, in quotes, that inhibition actions. And so we also talked about non-competitive, where now in non-competitive, we are not we are not having both binding to the active site. However, here we're having Vmax reducing, but because you know we're not really changing anything to the active site, increasing the concentration of the substrate will not change anything. That's why Km prime is the same in non-competitive. However, the Vmax changes. Okay. And so in uncompetitive, in this case, we talked about how in this case the inhibitor binds to the enzyme substrate complex already bound, right? And this is a scenario where we have both Km prime and Vmax prime decreasing, okay? And then next we went into Lineweaver-Burk, Hofstee, and his Woolf linearization plots. These are just ways of linearizing the Michaelis Menten equation, and then based on those linearized equations, right, we know what the slope, the y-intercept, the x-intercepts are, and then if we have a competitive versus non-competitive versus uncompetitive inhibition mode, we can pretty much draw or analyze or draw conclusions on how we expect the slope, the x-intercepts, or the y-intercepts to change based on what inhibition mode we are in and based on what the linearization type we're looking at, right? We kind of went over those different scenarios and those different plots. So that's something that you should also be familiar with for your exam and, play around with it and see how the graphs will change or the intercepts will change or what the line for, like what the typical plot for competitive in Hofstee versus competitive in Heinz Wolf will look like. It's also very important to know what, as a quick, reminder, just to know for each of these linearization types, what is your y-axis, what is your x-axis, because we talked about Lineweaver-Burk, right? That's the simplest one to remember. That's your double reciprocal plot. So you're literally just plotting 1 over V versus 1 over S. So like your inverse rate versus your inverse substrate concentration. So go back and understand and look into those linearization plots, and I've provided also the equations on how to linearize them. So that's something that will also be important to know for your exam. And then lastly, we went over our inhibition studies and how we can determine Ki, right? We talked about how once you get Km prime or Vmax prime, right? Based on how those are changing with respect to the inhibition mode that you're in. So we said for competitive, which was case 1 in the slide before this, we said Km prime would increase. So Km prime is equal to Km times alpha. And I showed you how to linearize that. And then based on that linearization, you can plot your y versus your x, right, from your linearization equation to get what your slope and your intercept will be. And then from that, calculate your Ki value. Same thing for case 2. We went over the non-competitive where we said now Vmax prime is reducing, and then we also linearized that, and then we said, okay, if you get the Vmax prime from your previous, linearization plots at the different inhibitor concentrations, and you plot the linearized y, what your y should be versus what your x should be. In this slide here, we said your y will be 1 over Vmax prime and your x will be I. So when you plot that using your slope and your intercept, you can once again, calculate for that Ki. And we didn't talk about the third case, which is the uncompetitive, but we said in the uncompetitive, the Vmax prime will typically be the same, right? Because your Vmax prime is in uncompetitive is also reducing. The only thing that will change now is that since your Km prime in uncompetitive is also reducing, your Km prime will literally follow this linearization format and not this, right? Because in this case, Km prime is increasing. In case 1, Km prime is increasing because that's for competitive. Okay. And I hope with all of this, I've been able to summarize, all the important parts about the enzyme kinetics that you need to understand and how they all kind of fit into each other, and how you can draw trends and analysis on what should change, how it should change. And I wish you good luck on your exams, your tests, your quizzes. If you have any questions regarding this lecture, please feel free to email me at learningwithfunke@gmail.com, and I'll be happy to respond. Yes, have a wonderful day.